In this video, we are going to study how to solve first order, first degree differential equations. In my earlier video, we have seen that equation x square plus y square equals r square represents a family of circles with center at origin and radius r. Here, since radius r takes different values, it is known as parameter or arbitrary constant. By differentiating this equation with respect to x, we have found x plus y dy by dx equals 0 as the differential equation which represents this family of circles. This is first order, first degree differential equation, and we are going to study how to solve this equation to get this equation back again, which is known as general solution for unknown radius r and particular solution for known radius r. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. By differentiating x square plus y square equals r square with respect to x, we have obtained this differential equation, and we know that integration is reverse process of differentiation. Therefore, by integrating this differential equation, we can get back this general solution. But this is done through specific methods known as methods of solving differential equations, and the first among them is variable separable form of a differential equation. We will see how to solve differential equation x plus y dy by dx equals 0 by this variable separable form. In order to solve this differential equation, we have to integrate it, but we cannot integrate as it is. For that, we first have to separate the variables. Now how this is done, let us see. First, we will multiply throughout by dx. That will be x into dx plus y into dy equals 0 into dx 0. Here we can see that variable x is with dx and y with dy. This is known as variable separation, and after variable separation only we can integrate this differential equation. Now we will integrate this. Integral x dx plus integral y dy equals 0. This will be x square upon 2 plus y square upon 2 equals constant of integration c1. Multiplying throughout by 2, this will be x square plus y square equals 2c1, which we write r square, where r is radius of the circle. This can be verified geometrically also. If center of circle is at origin pxyb, any point on the circle, and if radius is r, by distance formula cp square will be x minus 0 whole square x square plus y minus 0 whole square y square, and cp square will be r square, which is the equation of standard circle whose center is at the origin and radius equals r. So this is the general solution of this differential equation. Find general solution of differential equation dy by dx plus y equals 1, where y not equal to 1. It will be dy upon dx equals 1 minus y. For separating the variables, we write dy upon 1 minus y equals dx. Now the variables have been separated because function of y is with dy and constant 1 is with dx. Integrating 1 upon 1 minus y dy equals integration 1 dx. This will be log mod 1 minus y upon derivative of minus y minus 1 equals x, plus in place of constant of integration we will write log c. This is because we have got log on the left hand side. This will be log 1 minus y equals minus x minus log c. Taking log c to the left hand side, it will be log c plus log 1 minus y equals minus x. This will be log c mod 1 minus y to the base e equals minus x. C mod 1 minus y equals e raised to minus x. 1 minus y equals e raised to minus x upon c. Y equals 1 minus e raised to minus x upon c. Y equals 1 minus c1 e raised to minus x, where 1 upon c equals c1. So this is the general solution of this differential equation where c1 is the arbitrary constant. Find general solution of dy by dx equals 1 minus cos x upon 1 plus cos x. We will transform this rational function into a simple function by substituting 1 minus cos x as 2 sin square x upon 2 and 1 plus cos x as 2 cos square x upon 2. After cancelling 2, we get tan square x upon 2, which is sec square x upon 2 minus 1 according to a trigonometric identity. So dy by dx equals sec square x by 2 minus 1. Now the purpose of doing all this is to convert this function into an integrable form sec square x by 2 minus 1. So this will be dy equals sec square x upon 2 minus 1 dx. Now we can integrate this. So this will be integral 1 dy integral sec square x by 2 minus 1 dx. This will be y equals tan x by 2 upon derivative of x by 2 half minus x plus constant of integration c, which in the simplified form will be y equals 2 tan x by 2 minus x plus c, where c is parameter or arbitrary constant. So this is the general solution of this differential equation. Find general solution of dy by dx equals square root 4 minus y square, where y lies between minus 2 and 2. Separating the variables, dy upon square root of 4 minus y square equals dx, integrating dy upon square root of 2 square minus y square equals integral 1 dx. This will be sin inverse y upon 2 equals x plus constant of integration c. This is according to integral dx upon square root of a square minus x square equals sin inverse x upon a plus c, which can be written as y upon 2 equals sin x plus c, according to if sin inverse theta is x, then theta is sin x. So in the simplified form, it will be y equals 2 sin x plus c, which will be general solution of this differential equation. Find general solution of e raised to x plus e raised to minus x dy minus e raised to x minus e raised to minus x dx equals 0. E raised to x plus e raised to minus x dy equals e raised to x minus e raised to minus x dx. For separating the variables, we write dy equals e raised to x minus e raised to minus x upon e raised to x plus e raised to minus x dx. Here the function of x is with dx and constant 1 is with dy. Integrating, we write integral 1 dy equals integral e raised to x minus e raised to minus x upon e raised to x plus e raised to minus x dx, which is y equals log mod e raised to x plus e raised to minus x plus c. This is because we have a rule in integration. Integral f dash x upon fx dx is log fx. Here derivative of the denominator fx is in the numerator, which is f dash x. Here also derivative of the denominator, which will be derivative of e raised to x is e raised to x plus derivative of e raised to minus x is minus e raised to minus x which is in the numerator. So according to this rule, the integral will be y equals log mod e raised to x plus e raised to minus x plus c, which is the general solution of this differential equation where c is parameter or arbitrary constant. Find general solution of dy by dx equals 1 plus x square into 1 plus y square. For separating the variables, we will divide by 1 plus y square and multiply by dx. So it will be dy upon 1 plus y square equals 1 plus x square dx. Function of y is with dy, function of x with dx. So variables have been separated. Now integrating 1 upon 1 plus y square dy equals integral 1 plus x square dx. Integral of 1 upon 1 plus y square is tan inverse y equals x plus x cube upon 3 plus constant of integration c, and this is the general solution of this differential equation where c is arbitrary constant. Find general solution of y log y dx minus x dy equals 0. For separating the variables, we will divide dx by this x and dy by this y log y. So this will be dx upon x minus dy upon y log y equals 0. Function of x with dx, function of y with dy. The variables have been separated. Integral 1 upon x dx minus integral 1 upon y log y dy equals 0. Derivative of log y is 1 upon y. Therefore, we will solve this integral by substitution. So, integral 1 upon x dx minus, here we will substitute log y equals t. After differentiation, it will be 1 upon y dy equals dt. So after substitution, this integral will change into integral. For 1 upon log y, we write 1 upon t, and for 1 upon y dy, we write dt equals 0. Now we can integrate this. This is log mod x minus log mod t equals, we write the constant of integration log c because there are log terms on the left hand side, which is log x minus log of, substituting for this t log y, it will be mod log y equals log c. This will be log x upon log y equals log c. X upon log y equals c. Log y equals x upon c, which can be written as xa, where 1 upon c equals a, or y equals e raised to ax. This will be the general solution of this differential equation. Find general solution of x raised to 5 dy by dx equals minus y raised to 5. Multiplying by dx, this will be x raised to 5 dy minus y raised to 5 dx. Dividing dy by y raised to 5 and dividing dx by x raised to 5, it will be dy upon y raised to 5 equals minus dx upon x raised to 5. Dx upon x raised to 5 plus dy upon y raised to 5 equals 0. Function of x goes with dx, function of y goes with dy. So the variables have been separated. Integrating dx upon x raised to 5 plus integral dy upon y raised to 5 equals 0. This is integral x raised to minus 5 dx plus integral y raised to minus 5 dy equals 0, which is x raised to minus 5 plus 1 upon minus 5 plus 1 plus y raised to minus 5 plus 1 upon minus 5 plus 1 equals constant of integration c1 x raised to minus 4 upon minus 4 plus y raised to minus 4 upon minus 4 equals c1, multiplying throughout by minus 4, x raised to minus 4 plus y raised to minus 4 equals minus 4 c1 x raised to minus 4 plus y raised to minus 4 equals C. Writing C for this minus 4c1. Now this is the general solution of this differential equation where this C is arbitrary constant. Find general solution of dy by dx equals sin inverse x. For separating the variables, we write dy equals sin inverse x dx, function of x with dx and constant 1 with dy. So the variables have been separated. Now we can integrate. Integral 1 dy equals integral sin inverse x dx. We do not know integral of sin inverse x. So we write this integral as integral sin inverse x into 1 dx. Now we can integrate this integral by the method of integration by parts, which is first function sin inverse x into integral of second integral 1 dx minus integral of derivative of first means derivative of sin inverse x 1 upon square root 1 minus x square into integral of second, that is integral of 1 dx whole with respect to x. This is sin inverse x into integral of 1 is x minus integral of 1 dx is x. So this will be integral x upon under root 1 minus x square dx. Integral 1 dy is y, which equals x sin inverse x minus, we name this integral I1, we name this equation 1. We will solve this integral I1 separately. So we have I1 equals integral x upon square root of 1 minus x square dx. We can solve this integral by method of substitution. For that we will substitute for this 1 minus x square equals t. Now differentiating, this will be minus 2x dx equals dt. X dx equals minus half dt. Now for this x dx we will substitute minus half dt, and for this 1 minus x square we will substitute t. So this I1 will be integral minus half into dt upon square root of t. This is minus half integral 1 upon square root of t is t raised to minus half dt, which is minus half t raised to minus half plus 1 t raised to half upon minus half plus 1 half. Cancelling half, I1 will be minus t raised to half will be square root of this 1 minus x square. Therefore this equation 1 will be y equals x sin inverse x, this minus into this minus will be plus square root of 1 minus x square, and in the end we will add the constant of integration c. So this is the general solution of this differential equation where c is arbitrary constant. Find general solution of e raised to x tan y dx plus 1 minus e raised to x sec square y dy equals 0. First we will separate the variables. For that we will divide this dx by this 1 minus e raised to x, and we will divide this dy by this tan y. So this will be e raised to x upon 1 minus e raised to x dx plus sec square y upon tan y dy equals 0. Function of x with dx, function of y with dy. Hence the variables have been separated. Now integrating e raised to x upon 1 minus e raised to x dx plus integral sec square y upon tan y dy equals 0. We write this as minus integral e raised to x upon, we write 1 minus e raised to x in the reverse order, e raised to x minus 1 dx plus integral sec square y upon tan y dy equals 0. Now here derivative of denominator e raised to x minus 1 is e raised to x, which is found in the numerator e raised to x. Hence this integral will be minus log mod e raised to x minus 1 plus, Here also derivative of the denominator, that is derivative of tan y, is sec square y, which is found in the numerator. Therefore this integral will also be log mod tan y equals, in place of constant of integration we will write log c. This is because there are log terms on the left hand side also. This further will be log tan y minus log e raised to x minus 1 equals log c. That will be log tan y upon e raised to x minus 1 equals log c. This will be tan y upon e raised to x minus 1 equals c, or tan y equals c into e raised to x minus 1. So this is the general solution of this differential equation, where this c is arbitrary constant. The rule that we have used to solve these two integrals is integral f dash x upon fx dx equals log fx plus c, which means for a rational function, if derivative of denominator is found in the numerator, then integration of such function is log of the denominator. If you like this video, please like, share and subscribe this channel. See you in the next video. Until then, keep watching Number Collage. Thank you.